Einstein versus quantum mechanics. Who is right? Einstein's vision, a determined universe. Einstein believed the universe is like a perfect clock. Every motion, every event is caused by something else. If you know the present, he said, you can predict the future. His world was deterministic, no room for luck or randomness. The famous quote, God does not play dice with the universe. To Einstein, the universe followed strict laws, general relativity, cause and effect, mathematical certainty, the rise of quantum mechanics. But then, the world of the very small, atoms, electrons, started behaving weirdly. Physicists found that particles didn't follow clear paths. Instead, they acted like waves, probabilities, blurs. You couldn't say where an electron is, only the chance that it might be somewhere. This was quantum mechanics, a new theory full of strange, unpredictable behavior. The uncertainty principle. In 1927, Werner Heisenberg made things worse or more fascinating. He showed that the more precisely you know a particle's position, the less you can know its momentum. This became the uncertainty principle, not because our tools were weak, but because the universe itself is uncertain at its core. Einstein hated this idea. He said, God does not play dice. Quantum physicists replied, stop telling God what to do. Schrödinger's cat, a thought experiment. To challenge quantum weirdness, Erwin Schrödinger created a famous thought experiment. Imagine a cat in a sealed box. Inside the box, a radioactive atom, a detector, and a vial of poison. If the atom decays, the poison is released and the cat dies. If it doesn't, the cat lives. But according to quantum theory, until you open the box, the atom is in a superposition, both decayed and not decayed. So the cat is both alive and dead at the same time. Einstein found this ridiculous, but quantum physicists insisted this is how the quantum world works. Einstein's counterattack, EPR paradox. Einstein didn't give up. In 1935, along with Podolsky and Rosen, he published the EPR paper, a challenge to quantum mechanics. He described entangled particles, two particles that affect each other instantly, even if far apart. He called this spooky action at a distance. Einstein believed there must be hidden variables, unseen factors that quantum mechanics was missing. He said quantum theory was incomplete, but the quantum world refused to obey classical logic. Bell's theorem, the turning point. In 1964, physicist John Bell came up with a test. He showed that if hidden variables existed, they would create different results than quantum theory predicted. And then the experiments began. Over decades, tests were done around the world, and the results, quantum mechanics was right. No hidden variables, no local realism. Nature is fundamentally non-deterministic and entangled. Einstein's classical view had lost. So, who was right? After decades of debate and experiments, the answer seems clear. Quantum mechanics is right, at least for now. Its predictions have been proven again and again in real-world experiments, from atomic clocks to lasers, MRI scanners to semiconductors. Modern technology is built on quantum principles. Einstein's idea of hidden variables didn't match what nature shows us. He lost the scientific argument. But was Einstein really wrong? Not entirely. Einstein was asking deep questions. He challenged physicists to think harder and test things more carefully. His skepticism improved science, not weakened it. Even though he didn't agree with quantum mechanics, his work in general relativity, photoelectric effect, and more laid the foundation for modern physics. Einstein may have lost the debate on quantum randomness, but he helped science grow stronger. Can both be right? Here's where things get even more interesting. Quantum mechanics explains the very small, atoms, electrons, photons. General relativity explains the very large, planets, stars, galaxies, black holes. But they don't work well together. When scientists try to apply both theories to extreme places like The center of a black hole, the beginning of the universe, Big Bang. The math breaks down, the two theories conflict, so scientists are searching for something deeper, a unified theory that connects both worlds. Some of the leading ideas are string theory, loop, quantum gravity. Quantum gravity theories were still looking for the complete picture. The mystery continues. Even today, physicists are not fully satisfied. We can use quantum mechanics to build powerful tools, but we don't fully understand why it works the way it does. What is a wave function? Why does measurement cause collapse? Is consciousness involved? These are not just science questions, they touch philosophy. So, even though quantum mechanics wins in practice, the mystery remains. Einstein's original question, is the universe truly random, is still being asked in new ways. Finally, quantum mechanics is right experimentally. Einstein's local hidden variables don't exist. Based on Bell's experiments, Einstein was still one of the greatest scientists ever, and his challenges led to deeper discoveries. So, who was right? In the lab, quantum mechanics. In spirit, Einstein helped make it stronger. What's next? In physics, we now enter the age of quantum computing, using qubits and superposition to solve impossible problems. Quantum entanglement, particles connected beyond space black hole physics, where quantum and gravity collide. The search for quantum gravity. The final theory. The question now is not just who was right, but what comes next? If you found this topic interesting, like and share this video with friends who love science. Subscribe for more deep science breakdowns in simple language. Let us know in the comments, do you believe the universe is random or deterministic?